Hello everyone, welcome to COMP382, Language, Computation and Machine. This is the intro video. I'm going to just give an introduction to the course and what you are going to learn in this course and what you should expect from this course. All the details about about me, about the course, the assessment, exam, assignments, quizzes, everything is available in the course outline. You should download and check on Blackboard. So I'm not going to cover those stuffs here, just an intro about the course, the topics and everything. So this course basically is going to be the most abstract course in the whole curriculum of computer science, not only in UFV, in basically any computer science program, undergraduate computer science program in the world. So in this course, we basically are going to learn about computation, computability, and complexity. And in trying to actually just answer this question, that what are the fundamental capabilities and limitations of the computers. So basically we wanted to know that what is computation, I mean in terms of the in very abstract form, what is computation and what is a computer, no matter what hardware you are using, just this abstract notion of computation and computer. And based on that, what can be computed and what cannot be computed. So there are some problems that we cannot answer them at all. During actually this journey, we are also going to learn that some problems are going to be easier to solve. Some problems are harder. You need more computational power to solve them, and basically this kind of stuffs. So the main topics that we are going to cover in this course are going to be finite automata and the language that will be represented by them, which is going to be regular languages. We are going to spend quite a lot of time on this topic. And then we will move to context-free grammars. And again, the languages represented by context-free grammars, which are going to be context-free languages. Also, we are going to spend a lot of time on this one. And at the end, I'm going to give an introduction to the Turing machine. And if we had time, just briefly talk about complexity theory, PNP, and so on. Let's just see that if we had enough time for that one or not. But the focus of this course is on the first two topics here, the finite automata, regular languages, and context-free languages. For the textbook, there are actually many good textbooks for this topic available. But the one that I chose for this course is Automata Theory, Languages and Computation by Hopcroft, Motwani and Ullman. I have actually listed some other actually good textbook here, Michel Sipser, and the other one by Ullman et al. That both of them are great textbooks. So basically I don't say that the textbook that I chose is better. It is just the one that I chose. Both, all of them are going to work well, but all the slides, lectures, everything that I have prepared is based on the first one. Okay, so the rest of this video is going to just, again, I'm going to just give, basically explaining about, again, what this course is about. By taking this course, by passing this course, you will not learn how to program. You will not learn how the hardware works. But you are actually going to learn what is computer science, mainly as a science, not as a in terms of programming languages, or for example, in some technical stuff that you learn in other courses, or about the hardware. You have actually had several courses on all of those topics. In this course, we are not going to think about computer as any of those stuffs. You should not think about computer as the actual laptop, desktop, iPad, whatever that you are actually using. You should think about computer as a computer science, as a science. What in the past 60, 70 years people have been doing to contribute to computer science. So again, basically, I'm going to just repeat this question a lot of time. This is what we are going to answer in this course, that what kind of problems we can solve, we can compute mechanically. It doesn't matter what hardware you are using or what software, all those are going to be just the details. They're going to abstract away all of those details and just answer this question, that what problems can be computed, how fast, how efficient we can compute them, how much space we would need. For some of the problems are going to be much easier. You need less amount of memory. Some of them you need more memory for them, and these very abstract problems you are going to learn. So if you check the curriculum of other computer science programs, this course also called the Theory of Computation or Automata theory. So when we are thinking about the automata theory, as I said, when we are talking about a machine, a device, automaton is going to be a machine, a device. But when we are thinking about a device, we don't think about an actual computing device, a physical computing device. We are basically thinking about the model of computation. Okay, so all of those machines that we are going to discuss and describe, for example, the finite state automata or Push-non automata or Turing machine, they are all just computational model. We don't have any physical machine for these stuff. You can build a physical machine for them actually, but this is not something that we cover here. We just think about the computational model of those machines. So if you have this question that in mind, that what is the application of this course, I should actually answer it this way, that if you wanted to know how any computer works, you should learn this course. Basically, this course is going to help you to understand that how the computers works, because this is going to be basically this course in all BSc programs is the prerequisite for the compiler course. And in the compiler course, you will learn how we design a compiler, and basically you will learn how a computer works. If you wanted to know how a computer works, this course is a must. This is where exactly you would understand that how all of these actually other stuff that you have learned is going to work, what is behind them, what is the computational model behind them. There are plenty of interesting applications, except this fact that this, this is not magic. Computer is not magic. You shouldn't think about it as just a black box, because you are computer scientists basically, or you are studying computer science anyway. So it is going to not only tell you how the computer works, but also it has a lot of applications in designing compilers for different programming languages with different abilities. This is, this course is an application for computer architecture, designing computer architectures, different computers, or string matching in text processors, parsers. Basically, any parser is going to be a compiler. So all is going to be the same. So as I said, when we are going to actually learn about the computation models, we need to abstract away all the specifications of the machines, programming languages, and everything. So the way that we deal with a problem is that we think about a problem as a set of as a set of strings, and each instance of the problem is going to be represented using a string. Okay, so these are, as I told you, this course is very abstract, but this is the way that we are going to represent when we are actually abstracting away all of those details about the machine and programming languages and everything. We will think about any problem that you get, and for example, I don't know, checking if a number is a prime number, for example. Okay, this is a problem that you can just started, I don't know, Eclipse, any programming languages, and write a Java program, Python program, and whatever that takes as a number as an input, and just check that if it is a prime number or not, right? This is a problem. But how we represent that problem in this course, we represent the problem as a set of strings that each number basically is going to be a string. For example, you can represent it as any number as a string of 0 1s, right? Binary string. And any number is going to have a binary representation. This is going to be an instance of your problem, and basically the program that you write to solve the problem will be, you should think about it as a machine that you design, and you pass your input, that number in which is going to be a string, you pass it, and your machine, that program basically tells that does this program belong to that set, the set of all prime number or not? Okay, so this is the way that we represent the problems in this course. I'm going to talk about it more in the next lecture when we talk about the languages, strings, and everything. So just an intro that, okay, we are going to have an alphabet. An alphabet is going to be a finite set of symbols. For example, binary alphabet. You can actually have any alphabet, the alphabet of the English alphabet, or any program, or for example ASCII code as your alphabet, whatever. All of these are going to be an alphabet. So alphabet is a set of finite symbols that and then all of your input instance of problems are going to be some words, some strings, which is going to be a sequence of a finite sequence of these symbols. And then a language is going to be a set of these strings, or sometimes we call it word or sentence. It doesn't matter which actually name you choose, word, a string, or sentence. All of them are referring to a sequence of strings from your alphabet. A language is going to be a set of these sentences, these strings. Another actually term, I'm just trying to refer to all these terms here, define them. I'm going to formally define them in the next lecture. So just, mention them here as an intro. So a grammar is going to be, again, a finite set of rules, that these rules are going to define your language. So all of the sentences in that language will be generated using a grammar. So don't worry if you don't be confused by these terms. I just wanted you to, get used to these terms. And these are the terms that we are going to refer to them, work on them a lot I mean, the whole course is over these terms. So let me actually give you some example of, again, a problem. So as I said, we are going to represent a problem here by a language, which is going to be a set of strings. For example, think about it, this simple problem that a set of binary strings that ends with a 0, okay? I can actually, in a regular basis, if for example, in a course like Introduction to Programming, you would see this problem as, okay, write a program that takes an input string, a binary string, and check if the last symbol is 0. Okay, so that problem here will be represented in this way, that the set of all binary strings that ends with a 0. So any string that you get as input either belongs to this set or not. If it belongs to the set, you would actually answer yes. If it doesn't belong, the answer is no. Right, so this is the way that we represent a problem here. And so, yeah, you know that we can simply answer this problem, or many other actually problems like this one that works on the strings. Okay, so a more complicated problem, for example, the set of binary strings that represent a legal Java program. Okay, basically a Java program that doesn't have syntax error. Can we solve this problem? You can see that this problem is exactly the problem that the compiler solved, right? You pass your source code to the compiler, and compiler, for example, the compiler of Java will compile it and check for the syntax error. If it doesn't have any syntax error, not only actually it tells you that yes, there is no syntax error and everything is good, basically compiler does more. It actually just will parse it and convert it to bytecode, right? It actually does more than just checking if it is a legal Java program or not. But anyway, this is a problem, and this is the way that we represent it: a set of all binary strings that represent a legal Java program. And your input, you can just think about it in this way, that your source code will be, in fact, a binary, binary string, right? Because your source code is a sequence of symbols. All those symbols has a binary representation and ASCII code, right? And if you just think about your program as a sequence of all those binary representation, binary numbers, it's going to be one string, right? A very large, long string. But anyway, this is going to be a one string. So yes, this problem is also solvable. The next problem that I'm going to show you, but you can see that this problem is much harder than the previous one, right? I'm just trying to give you some, an insight to what we are going to do in this course. We are going to learn about different type of problems, some of them which are simpler, some of them which are more complicated to solve, and let me actually show you another example. The set of binary strings that represent a legal Java program which does not contain an infinite loop. So in other words, I can actually tell you that you wanted to check if there is a an infinite loop for example, in a Java code or not. Right? Can we solve this problem? Basically, this is the problem, and the answer actually is that no. This is the type of problems that, one of the problems that, because basically there are millions of problems that we cannot solve. If you think about it, in fact, there are most of all possible problems which exist, we can't actually solve them. Most of them, they're just a small number of problems are really actually solvable. So yes, the solution, the answer here for this question is that there is no way that you can solve this problem. There is no way that you can check if a Java program does have an infinite loop or not. There are some hacks that might actually detect some type of infinite loops. If you check it online, this is a problem that people are very interested in, and you can actually find many interesting results if you search it in Google. But anyway, there is no way that you can write a program that to check another program, some input program does have a finite infinite loop or not. So these three examples basically just give you the whole idea that what we are doing in this course. What problems can be solved, what problems cannot be solved, what problems can be solved efficiently, easier, what problems would take more time, more power, more computation power would need to be solved, and so on. Okay, I like to basically talk about the Turing machine briefly here as well. All of you have learned about the Turing. I'm almost sure that at least if not in the context of computer science, probably most of you have heard about that movie, the Imitation Game, about the Alan Turing. Alan Turing was a British scientist who actually invented the Turing machine. In fact, the work that he did over the Turing machine, the model that he invented, and his thesis has been done actually before the whole topic of that movie, the Imitation Game, that Enigma machine, and so on. The Turing machine was actually before that, so it is not about the topic of that movie at all. So, okay, forget about all these stories. So what is a Turing machine? Basically, I should tell you that the most abstracted form of a programming language, a computer, is a Turing machine. Okay, and so what is a Turing machine? A Turing machine basically is going to be a control center, which is going to be a very simple automata. There is going to be a tape, which is divided to some cells. We would assume the tape is infinite, although this is not practical, but this is just a computational model, right? So this is very abstract, so you can assume that you have infinite space here. So that we have divided the tape. You can actually see the tape here. The tape has been divided to some cells. Over each cell you can actually have a symbol. You can, and there is a head that can read and write over the cell. Okay, and that control machine basically just control this head that go to the left, go to the right, or read from the tape or write something over the tape. Okay, so that's it. This is the whole idea of a Turing machine. And it is interesting to tell you that any programming, any computer that we can design, I mean, in the way that the computers that we have right now, and programming languages with the most powerful actually GPUs, CPU, whatever, lots of memory and so on, all of them are actually a model of a Turing machine. In fact, you can, if you abstract away all the details of the hardware and software programming languages and everything else, all the computation model is going to be the same as the Turing machine. So basically any program that can be solved using any computer, computer that we have, any program that can be solved ever can be solved using a Turing machine. And this is actually a nice idea behind that although the machine that I explained to you is very simple, all the power that it has and the space memory that it has access to is just limited to a tape and just going to the right and left and just writing or reading over the tape. This is all you need basically to be able to solve any problem. It might actually take a long time, definitely, because the machine is very simple here, but in terms of the computational ability, you cannot actually do more than what a Turing machine can do. So remember that problem of finding an infinite loop in a Java program or any programming in any source code. That problem is not solvable. It cannot be solved in any computer. Basically the main proof is over the Turing machine, because it's going to be very hard if you wanted to prove it using a general machine. All those proofs to show that a problem is decidable or not, we can actually solve a problem or not, we do it over this simplified computational model. Okay, so I think I have been talking about this Turing machine a lot, and I don't want to actually, because this is going to be the last lecture of this course, I'm going to talk about the Turing machine, and you would learn about it in more higher level courses on the computational model and this topic if you are interested. Basically, usually in graduate schools, but not in this course anyway. So the last thing that I'm going to talk about is the Chomsky hierarchy. You might actually heard about this name, Chomsky. Chomsky is in fact a linguist, but he actually invented this hierarchy, which is going to be the main hierarchy of the computational model. So all the different models that we have with different powers are a part of actually this hierarchy. So the first level, the simplest actually level in this hierarchy is called the finite state machines or finite state automata, corresponding to regular languages. So many problems, although this type of machines has a very limited power, but still they can actually solve very interesting problems. And basically finite state machines are going to be the first topic of this course. We are going to talk quite a few weeks over, I spent quite a few weeks over the finite state machines. The next level in this hierarchy is going to be context-free languages. Don't be confused with programming languages. Whenever I'm talking about a language here, I'm talking about a problem basically. So forget about all the programming languages in this course. We are not referring to any of them. So a context-free language, this is going to be another level in this hierarchy. The type of machines that actually solve the problems belong to this set, this hierarchy, is going to be called push-down automata. Basically, they are more powerful than the finite state machines because they have access to some memory in a form of a stack. But don't worry, we are going to again spend quite a lot of time over context-free languages, push-down automata, and all the properties of these languages, problems, and so on. So basically all those problems that belongs to this hierarchy, this level in the hierarchy, are more complicated, harder to solve than the problems that belong to this level. After the context-free languages, the next level in the Chomsky normal form, basically I have abstracted away again this hierarchy, and the next level is going to be Turing machine. So basically all the problems that we can solve is going to be a part of this level. So this level has, after this level, it's going to be the problems, the undecidable problems, the problems that we cannot solve them. mechanically we cannot solve them. We cannot write use a computer to solve them. You as a human can solve them, but not a computer. When I'm saying we cannot solve them, it means that we cannot use a computer to solve them. We cannot write a program to solve them. Those problems that belongs to actually this set in the Turing machine that I wrote here, as I said, I have abstracted away many other actually levels here, but you would have a level for the polynomial numbers, for NP complete numbers, NP hard and exponential problems, and so on. So there are a lot of actually levels here, but again, they are not going to be the focus of this course. So I just put the Turing machine over all of them. But you can actually see that if a problem belongs to this set in this part of the hierarchy, but not here in the context-free languages, so this is going to be definitely harder than this those problems which are a part of the context-free languages. The context-free languages, for example, a compiler, when you are designing a compiler, basically you are defining one of the problems in this set. So although it might actually look very complicated to write a compiler, but it is as easy to be solved in this set. So it's not actually in the higher level in this hierarchy. So all the compiler designs will be a part of actually this level. Finite states, anyway, so from the next week we are going to actually talk about the finite states. You will see what type of problems can be solved by finite state machines, although the machine is basically very limited in terms of the computational power. Yeah, I think that's pretty much everything that I wanted to actually talk about this hierarchy and what you are going to learn. So basically we are going to focus on finite state machines and then context-free languages, and just briefly talk about the Turing machine by the end of the semester. This table here, just basically I tried to summarize the history of the computer science, where a computer science basically as a science has started in 1930s by Alan Turing. He for the first time actually just designed the Turing machine, talked about the decidability, undecidable problems, halting problem, and in 1940 1950s, Noam Chomsky basically invented that hierarchy, talked about the finite state, and then context-free level and different levels of the computation. By the end of 1960, actually many people actually started working on the NP complete, and Cook actually introduced the problem of intractable problems and NP hard problems. And in 1970s, basically the modern compilers and the what we are really calling a computer has invented for the first time. Before that, whatever has been actually discussed was more like some computational model, some abstract theoretical discussions, not real computers, although they have invented some machines as well. But anyway, those are very limited powers and very they didn't really used in real world. So that's it for this lecture.